And your environment is not necessarily of measure-like type, of Q&D or however you want to call it, yet the final result is that you are being measured. Even if you know there is no apparatus actually measuring you, and there is no such Hamiltonian between you and your environment. Because this is one of the key points in the argument. So why should the environment act as a measuring apparatus causing continuously the collapse? If, you know, being a measuring apparatus means to have one such Hamiltonian. I mean, why shouldn't it be the one I wrote before? Which is actually, we know it's a very accepted Hamiltonian. So this is essentially the topic of the talk. So this is a situation. We are going to consider two systems, gamma and psi. And as Philippe mentioned at the beginning, there's no need to call it apparatus at all. It's just another quantum system. Gamma is going to be the observed system and psi is going to be the other system. Then what do? Well, we start thinking, what if this psi is not just one simple, quantum system, but is something which is made by a large number of quantum systems. And, well, in general, you can't say much about this situation, apart from the fact that you can have an extremely complicated interaction between each particle of psi and your principal system. So we have to add an ingredient, and the ingredient is, what if not only this is made by a large number of particles, but it also behaves classically. And I will better explain what I mean by that. So if you add this condition, which is not necessary, I mean, the fact that the system is made by a large number of particles doesn't mean by itself that it behaves classically. We very well know this. There are plenty of macroscopic quantum systems. Okay, so we really have to add this condition. If we add this condition, then, and this is the end of the word, we will show that actually the behavior of this system is effectively that of a measuring apparatus, and that's why I tend to call it measuring apparatus. We will do this by concentrating actually on this system psi and studying the dynamical map I mentioned before. So the way the dynamics goes from the initial pure state of the principal system to the final state of the apparatus, which is obviously going to be a mixed one, so it's going to be a density operator. And we will show that the map, which is in general not of measure-like type, so this connection has nothing to do in general with the one I wrote here, in these limits, large N plus classical, actually becomes always equal to the one corresponding to a measurement. See the logic, please?
Yes.
This characteristic of behaving classically is something that can be attributed to the environment only, or to the environment when it is interacting with the system?
To the environment only, and I will show you how. So again, I'm sorry that I will probably have no time at all to end the talk, but still I think it's important I explain what I mean. You forgive me, okay? So let me explain what we mean by classical and quantum. This is something essentially taken from quantum field theory. So what is a classical theory? A classical theory is a phase space. What is a phase space? Is a manifold, okay? Differentiable manifold. With a Hamiltonian and Poisson parenthesis. What does it mean? In order to define a classical theory, you first of all need to give a phase space. Each point of the phase space is a configuration of your system. The dynamics is given by the Poisson parenthesis, which is something well defined, and by the Hamiltonian. Okay? Now, what is a quantum theory? The quantum theory is a Hilbert space Let me put it like this. A Hamiltonian, which is now not a function defined on the manifold, but an operator acting on the Hilbert space, and then the algebra. Okay, so bosons, fermions, well, fermions is not the algebra, but then might spin SU2, whatever. I mean, the kind of system that you use to write the Hamiltonian. So, let me just explain also what I mean by algebra. Possibly the algebra is the vector space found by some generators, which are called the generator of the algebra. For instance, if you consider bosons, these are just and this is usually called H4. I'm just defining this because I will get back to them. And this is SU2. And you have the proper parentheses for the two algebras. So the spin commutation roots and the bosonic commutation roots. And you can make it more general.
For bosons, why don't you consider also more products of N and N?
Pardon?
For bosons, why don't you consider more products of N and N?
I mean, these are enough to close the algebra. Okay, so an algebra is just defined by, I mean, the generators are those that close up. If you want to consider A and this, then you have what is called H6. It works. It's another algebra. It's called H6. And it's also closed. So if you write the commutation of all these operators with themselves, you remain inside the set of operators.
Okay, but why don't you consider, so then you can go on, I guess, and put more products, A power N or whatever. So why do you stop here?
Because it's not easy if you get, I mean, if you get R, it's not easy to define the algebra.
Yes, but typically you can get what people call non-linear processes. If I want to do squeeze line, I need a square.
Yeah. Okay. So you have to define a different algebra. You can define whatever algebra you want. Okay. Just have to find it. To find the algebra to which your systems belongs, it means that you have to find the operators such that if you commute them with each other, they don't produce a new operator.
What you tell later will not depend on this is 4-element algebra. I can use bigger algebra.
Yeah.
Yes, of course. No, these are just examples.
So you're explaining the construction.
Yes.
And in this case, you will do for H4.
Yes. I mean, you can have, and you can actually, I mean, I don't want to be too technical, but if you want to consider all the powers of the generators, then is enough to consider what is called the universal envelope of the algebra, which means that you take all the powers of the original generators. It's just to say that, you know, you have your Hamiltonian, it has a specific form, and that form of the Hamiltonian tells you what is the best algebra to use in order to describe your system. And obviously you tend to stick to the smaller one.
Best means Occam's razor.
Okay. So, essentially, when we speak about quantum systems that behave like a classical one, this means that actually you formally need to define this manifold, this Hamiltonian, and this Poisson brackets. So it's not just a way of saying, it's a formal part. You have your quantum theory with your Hamiltonian, your Hilbert space, your algebra, and you want to move into defining a manifold, a Hamiltonian which is a function on the manifold, and a Poisson bracket. Okay?
Is it just my context?
Pardon?
Is it just
it is.
It is my context.
It is.
That.
No, I mean, I think, just to be clear, I think what I'm going to say has a lot to do with what Philip was saying in a sort of mathematical format. Okay? I already, that's the reason why I gave that paper to Alexa, because I think it's strongly connected, but there is a sort of strong mathematical construction.
I also, this reminds me somehow the file quantization, but you are somehow doing the dequantization, the unquantization,
okay,
classicalization.
So one point that emerges from this treatment, and is actually one thing which is very seriously considered at the moment in people doing quantum field theory, is that actually you should never quantize a classical theory. You should actually get the classical limit of any quantum theory. So for instance, if you speak about relativity, general relativity, the viewpoint of quantizing the classical theory is tricky, and it might be completely wrong, simply because elementary systems are quantum. And so what you want to see is why a quantum system emerges with a classical behavior and with a classical theory. Not why a classical theory, if you put heads on variables and transform them into operators, become a quantum system. That doesn't make much sense. So this is actually the viewpoint that is now emerging on people working on these things, which is actually to see how the classical behavior emerges. So for instance, quantum relativity is the classical expression of a theory that no one actually knows yet what it is, which is originally quantum. Okay?
I would disagree with that. I think you need both from the beginning.
You need both to create the connection. So in order to understand what is the quantum theory that will go into the classical one you're looking, you need both. But, you know.
Yeah, no. Just that at that point in history, it made much more sense to ask how do you get the quantum from the classical. But now in this time of history, exactly. It makes more sense to ask the opposite.
Well, let's say, I think everyone has the right to stick to his own opinion on this. This is almost interpretational. But there must be a way to connect a quantum theory into a classical theory to see how it goes into that. Okay.
Yes, no, no.
So this is essentially the scheme of the talk. So now I'm sorry, but I have to become slightly more technical. So this is the idea. We start with the true dynamics. What is the true dynamics? We don't know. We just know that there exists a Hamiltonian that describes the interaction between my observed system that has appeared. So he's there. My observed system, which is at the moment in both positions. Back. I have projected him back there. Okay. So there is an interaction between my observed system and something else. Let me call it again apparatus. Forgive for this. And I don't know anything about it. Okay. So I just write it as general as possible. However, I know that at any time there exists a very nice and powerful theorem in linear algebra, which is called the Schmidt theorem, that allows me to write whatever state at any time t in this form. This is called the Schmidt decomposition. Shall I be more precise? You all know what it is? Okay. So essentially, you see, it's a very similar structure with respect to the one I wrote before. Why do I call it Tau-Schmidt decomposition? Because this decomposition is not general. It only holds for a given tau. What does it mean? It means I have a certain time t. For this state here, I can write it like this. If I change the time, the coefficients, the states, and these states, they all change. Okay? So it is not something, the Schmidt decomposition depends on the state. So if the states depends on the time, then the Schmidt decomposition depends on time.
It is also non-unique.
Pardon?
It's also non-unique.
It's also non-unique. Although in the case I will use, we will just take one of them. It doesn't matter whether it's one or the other. Okay? Key point is that these objects here are also normal basis for the Hilbert space of gamma and psi. You see the notation should be suggestive of that. So these are orthonormal bases. Okay. Good. So the map I want to study is the one, dynamical map. What is a dynamical map? Very simply, it's a linear map going from one density operator to the other one. It doesn't even necessarily goes from the density operator of one system to the density operator of that same system at a different time. It can connect density operators of different systems, as it is the case in here. Okay, so using the Schmidt decomposition, the dynamical map describing these dynamics reads like this. You simply have to write down the projector of this state, as I did before here, and you then partially trace the apparatus and you get this result. Okay? So this is for whatever Hamiltonian. So what is the point now? I can ask, because this is, as I said, is very similar to it's actually the same as the one I wrote here before. So it could actually be a measure and prepare map, although I made no assumption on the Hamiltonian whatsoever. So what's the point? I must ask myself, does it exist an observable, or gamma, which is the operator I wrote before, such that actually this map here is the measure and prepare map relative to that observable? Understand the point? So I started from a very general Hamiltonian I know nothing about. I write down the dynamics, I use Schmidt decomposition, I write down the map, I get a form that is suggestive of a measure and prepare map, it seems the same, and so I ask myself, so is this actually the effect of a dynamics of a measure-like type? Which means, does it actually exist an operator written like this, that if I put it back in the Hamiltonian as I wrote it before?
So it's a sort of...
Right, so does it exist?
You need to find also a O psi. You said, does it exist O gamma, also, but there should be also the other O, so your question implicitly means that I look for both of them, or?
It is enough that O gamma exists, because then I can define an O psi. Okay?
So it's an answer,
but
basically.
At the moment it's just an answer, a question, sorry, it's not even an answer.
Like try.
Please.
Excuse me, I don't understand from my thing, but this is to the Hamiltonian view as an operator.
Yes. Hamiltonian is an operator.
Yeah, but view as an operator.
Yes, yes, yes.
For that equation to be true.
Sorry?
For that equation to be true, you have interpreted the Hamiltonian as an operator, acting not as only an energy distributing device, but as an operator.
Absolutely.
From creation and function.
Yeah, I mean, this is what I meant when I said that the quantum theory is defined by a Hilbert space, a Hamiltonian meaning an operator acting on the Hilbert space.
Exactly.
Yeah. Okay. However, the answer is no. And why it is no? Well, essentially, because if you get back to, let me write it back. So what is the point in the measure and prepare men? Perhaps I wrote it with the capital Xi. So the point is that these coefficients, okay, must be the same as these ones in order for the map to be a measure and prepare map, which is something which is perfectly demonstrated by taking this Hamiltonian with O gamma written as it's written like that. But in general it's not true. Okay? So in other terms, the Schmidt coefficients, which are these coefficients here, need not be the same coefficient, entering the linear combination of the initial state you are measuring with respect to the basis gamma, which makes this absolutely meaningless as far as the measurement process is concerned. Okay? I've lost you.
We want to see the next steps now.
Okay, so, you trust me. Okay, the true dynamics is not describing a measure and prepare map. Okay? Now, what we decided to do is to build a measure and prepare map, meaning a measure like dynamics, as similar as possible to the true dynamics. So this is the idea. And how we do it? We take the ingredients of the Schmidt decomposition and we build it by hand. So we prepare the apparatus in this state here. You see all the ingredients are given. You defined an operator in this way, and we defined another operator in this way. We can do it. Okay? This is just a constructive approach. We have the ingredients and we build these three elements. Initial state of the apparatus, the operator of gamma and the operator of C entering this Hamiltonian. And then we go on making some calculation. And this is okay, you get all your dynamics, you make all your calculation. What is the problem? Is the problem that at the end you have the correct, okay, so this is the map we've built. Okay? So we had, yeah. So you see this is, okay, sorry. So this is the map we've built. Unfortunately, these states here are not the orthogonal one necessary. So if you write down the explicit form of this map, then you get some phases and you have some terms that you wouldn't like. So it's not diagonal. So in a sense, this map here has the correct coefficients, but has not the correct form. And so essentially the two maps are different. So now we have two maps. They are different. One describes a measurement process, but not with the correct states, and the other one does not describe a measurement process. And now what we want to show is that the two maps become the same in the limit I mentioned at the beginning, large N and classical. Happy? More or less? Well, you can trust me with the calculation. We can, later on we can go through. Just take this message. The two maps are somehow similar. They have elements in common via the Schmidt decomposition, but they are not quite the same.
But if you just take some asymptotic time limit, that is you run your then you enter the substate, and then you do the Schmidt decomposition just at the end.
It doesn't work. Also because if you don't introduce some more hypotheses, there is no, in this kind of dynamics, which is perfectly unitary, and I've done no hypothesis whatsoever on psi, there's no reason why there should be a large T limit. This is going to be a periodic dynamics. It's unitary, it's periodic, unless I introduce some condition on the environment, like being very large and having a lot of different frequencies and so on. Which
you do it at the end.
Exactly, but not here. Not here. Okay? And you have to do it properly because it's not necessarily a large T limit. That is just one case. It could be something that happens immediately. Okay, never mind. Okay, so message, the two maps are different. The two dynamics are different. We already knew it, but now we have at least one map, so one dynamics that has the form of a measure-like dynamics, that has some elements in common with the original dynamics. Now I have to go through the tough part. So I have to see when and how and why a large N limit of a quantum theory can possibly flow into a classical theory. And I put all this if, when, why, because it's not, again I say it, it's not natural. It's not enough just to let the number of elements inside to grow in order to get a classical behavior. Now, in order to do this formally, we use generalized coherent states. We've learned this again from mathematicians. Generalized coherent states are a wonderful, very powerful tool, and I hope you will like them at the end. So, they essentially are the tool via which this connection is made. So you connect a Hilbert space with a manifold, a linear algebra with a geometrical structure via these states. And that's the reason why they are so relevant in the classical, quantum to classical transition. How are they built? So, this is the idea. You have your quantum theory, which means, as I said before, that you have your algebra, your Hamiltonian and your algebra. And you know that by exponentiating your algebra, you get a group. To make it simple, you have the group of all the possible propagators of your theory. It is a group because if you combine them, they are again propagators. So this is what is usually called the Lie group of your theory. Okay, so you have your algebra, you have your group. So you start with your Hilbert space, then you have your, Hilbert space, then you have your Hamiltonian, and the Hamiltonian defines your group G, which is usually called dynamical group, because it contains all the propagators. Then what you do, you fix an arbitrary state in your Hilbert space, and then what you do, you divide your group into the bunch of operators that act trivially on your state, meaning that they only give a phase factor, and all the others. All the others form what is usually called the coset. Okay, so it's you have your group and you take all the operators that act trivially on your reference state R, you see here, and then you take all the others. All the others are those that generate your coherent state when applied to the reference state. So this is essentially the main idea of the construction. This construction, which is called the group theoretical construction of coherent state, allows you to demonstrate that when you do this procedure, you not only obtain the coherent state, but you also define the manifold and a measure on the manifold. So this creates a connection between your algebraic structure, Hilbert space, Lie algebras, and so on, and the geometrical structure, which is typical of classical theory.
Sorry, what is D?
D are the operators, other from those that act trivially on the arbitrary state. Okay? They are usually called the displacement operators. Okay? So these are the operators acting non-trivially on R. Just to make it simple, if R is an eigenvector of a given operator, like you take, for instance, the spin-down state as reference, and then obviously Sz is going to be a trivial operator. If you apply Sz to that state, it only gives you a phase factor. So the displacement operator are going to be all the exponentiation of S plus and S minus, exactly as you build, the normal coherent state. No, sorry.
I don't know
Wait.
So it seems to say that all non-trivial operators are displacement operator, which is
once you've chosen a reference.
But if you just take a standard quantized electromagnetic field, if I start from vacuum as a reference state, I can go to any coherent state, but I can do many other things. I can squeeze, I can.
That is the typical. Squeeze. How do you obtain squeeze? You obtain squeeze by applying a displacement operator on the vacuum, and the displacement in this case is just.
Operator, so it's a not a.
It's just in general. You call displacement operator the one for field coherent state, but they are called displacement operator for whatever algebra. So for instance, the displacement operator for SU2 is e to the eta s plus.
For instance, the operator with Heidegger, you will call it the displacement operator?
Yes, they are all called displacement operators.
It's a little bit
tricky.
There is still a strange terminology. I would never call that displacement. Displacement is alpha.
For you, it's just the one. I mean, the problem is the same reason why I call this generalized coherent state. I mean, people working on this, they call them coherent state. When I call them coherent state, people always think about the field coherent
so
state.
I generalize that, then I call them symplectic operators.
Well, symplectic.
It's second order with unitary transform generated by quadratic form.
Yeah, I know. But again, in this way, you restrict to that case. Just take it as general as possible. You know, you can have also a to the fourth, a to the fifth, s plus, of course. Yes, because this is what they do. They displace.
No, but you use it.
No, I mean, but the reason is very clear why. These are the only operators actually displacing your state. You know what? I mean, it's written here. All the others,
yes.
Okay?
But it's just the name, again, it's a problem of terminology. I don't call that displacement because displacement is displacement.
But that's a problem of the community working on atom and bosonic systems. I mean,
if you call any operators which is not trivial displacement operator, any quantum optician will be completely.
Yes, but quantum opticians are not the only community.
Yes,
okay. Sorry.
Yeah. It seems to me that so you're recovering the manifold just as a portion of your group,
exactly.
But there is already group.
Yeah, and actually the so-called quotient theorem is very much used here because in principle G over F is not supposed to be a manifold, but there is a theorem because it's not a subgroup, it's really a quotient. Okay? And so in principle it's not a manifold. But there is a theorem saying that a quotient is actually a manifold, and using that manifold is exactly the quotient.
So a toy model, a baby example of your construction would be SO3 and the sphere S2.
Yeah.
You recover S2,
exactly.
SO3 quotient.
Yeah.
Quotient by
the rotation.
Exactly. SO2.
Yeah. And you can do it very general. For instance, in this way you can construct coherent state for SU11, which are actually the manifold is the Minkowski space. So, which are very interesting for people doing general relativity. So now people doing general relativity, they are working a lot with this stuff because the manifold is exactly the Minkowski manifold. Yes, okay. Never mind. I will never finish this talk, yes. But I think it's better like this, isn't it? Yes. Okay, good.
I have a question that I'm sure is related to the other one, but perhaps...
okay. Yes, so.
Perhaps I need to hear it a different way. So, generalized coherent states omega are different from R.
Yes.
Then how come you can have the last expression? Because I understand.
What is this expression?
Yes, to be a complete system of basis.
What?
The fact that this operator is this is the unitary operator, right?
D is not unitary.
No, the last.
Oh, the solution of. So I didn't mention about this yet, but
so R is not in omega.
R is in omega because it's actually generated. It's one of the. It's a coherent state because it's generated by 0. So it's actually the state that flows into the origin of your reference frame in the manifold. Okay. So R is a coherent state.
D is not unitary.
No.
I mean, sorry.
Sorry, D is unitary. Sorry. Otherwise it wouldn't be. No. Sorry. No, what I wanted, in fact, I had in mind something else I have to say, which is that omega are not also normal. Okay?
Omega, but
So the coherent states are not orthonormal. So actually this resolution of the identity is a very peculiar one. So it holds and it can be demonstrated, although these states are not orthonormal. They overlap.
And although there's one state which is R, which is not there.
No, R is there. It's in the origin of the manifold. R is definitely a coherent state because it's... sorry.
No, sorry, I don't understand that. Omegas are coherent states. R is also.
Yes.
Omegas are different from R.
Yes.
Then I don't understand the last expression. Why the integral of all those operators can be...
Equal to 1, it is demonstrated actually. But I mean, it's just...
The standard quadratics way to look at it is you start from vacuum, you displace the vacuum anywhere, this is D, and then you get a set of all coherent state, and it is an overcomplete basis, which is represented by this closure relation, but they are not orthonormal. So this is my standard picture.
Essentially, this is the usual continuous variable resolution of the identity. It's nothing special. The only special thing is that these are not orthogonal.
Okay, but omegas are not orthogonal to R?
No.
It's already true for standard space.
Okay. So the usual phrasing is that they form another complete basis.
Paola,
Tell me.
can I ask you to send a sort of conclusion message from now to what remains, because we are getting to...
I just want to, okay.
Yes.
So I just want to show you some examples.
Yeah.
So the key point, well, I want
please can you use your microphone?
Yeah. So essentially when you play this game, what you can, I just skip here. So let me think the best way to say it. Okay, with these two, with this generalized coherent state, you can actually give, and this was done in the 80s by quantum field theorists, conditions such that if these conditions are fulfilled, and these are very nice conditions actually with a lot of physical meaning, but I don't have time to discuss about them now, if these conditions are fulfilled, then the theory flows into the classical one. Okay? So, one of the things that makes this to happen is written here, and essentially what it means that this coherent state, they are not orthonormal, as we said before, and they overlap with almost everything. So if you just take one coherent state and you look at the overlap between the coherent state and any other state of your system, they overlap. So they seem a little bit useless. But when you implement the conditions so that the theory flows into the classical theory, the magic happens and actually they become orthogonal and they only overlap with one other state. So this is what I mean. This is the case of bosonic coherent states, so the one that Philippe is more familiar with. So you see here what he calls, the displacement is here. And then the manifold is the QP plane, and this is the measure. And I don't know if you can see it here. Here it is the overlap between the coherent state and the Fock state. And you see that if you move into the large n limit, which is going from here to here, with the condition ensuring that you are working with something that is flowing into a classical theory, then you see that only one line remains. Okay, so it really shrinks. If you take two different Fock states, n plus, you see the same game, and what is interesting is you see that the overlap never cross to each other. So either the coherent state overlaps with one Fock state or with another. It never overlaps with both of them. Just two of them. And this not only holds for Fock states, but also for other states. Like, for instance, these are cut states, and you see the same. I mean, the overlap is never simultaneous. And you have the same picture with magnetic spin systems. So with the spin coherent state, where you have the same structure, you see the displacement is here, the manifold is the unit sphere, this is the measure, and again you see the same. So what happens is essentially that these coherent states, when they move into the classical limit properly, they behave in a very peculiar way. Now, to make it really short, the point is that if you use this property, this is the end. So if you use the properties of coherent states to describe your problem in the classical limit, you see that the two original map actually formally, mathematically become the same. So, okay, so essentially, if you ensure your system that is the environment, the apparatus, whatever is looking at him, is a quantum system made by a large number of quantum particles behaving classically, then no matter the kind of interaction between this object that surrounds him and himself it's going to behave as a measuring apparatus, formally, mathematically. So this is the message. Sorry, I have to read.
Very good. So thank you. This talk has been very, very exciting, and we have a long discussion already. And I think we should continue discussing at the coffee break. And I want to make a little proposal so people that are presenting here or interested in what they are seeing, it's coming the idea to make a school. We should make a school, because this could explain further what we saw in the school of quantum logic, the input of Philippe. So I wonder if you would like the idea of organizing a school in the future. Well, let's think about it for now. And we start the next session in -5 minutes. Okay.
Sorry, it's my fault.
No, okay. Thank you.